At launch, this piece of foam weighed less than a laptop. 82 seconds later, it struck Space Shuttle Columbia's left wing. 16 days after that, the shuttle and all 7 astronauts were lost during reentry. So how could just 1.67 pounds of insulation destroy a spacecraft? And why did NASA believe the strike was safe? The answer begins with something that looks almost harmless. Columbia launched on January 16, 2003. The orange external tank beside it was covered in insulating foam. That foam kept the tank's cryogenic propellants at the right temperature and limited ice formation. Near the struts connecting the orbiter to the tank, thicker hand-shaped ramps of foam smoothed the airflow. At 81.7 seconds after liftoff, a large piece broke from the left bipod ramp. Camera footage showed it crossing the gap and striking the underside of Columbia's left wing. The video can be deceptive. The foam seems to fly backward. It didn't. Just before separation, the foam was moving with the shuttle at roughly 1,568 miles per hour. Once loose, air resistance slowed the light, blunt object very quickly. Columbia barely slowed at all, so the wing ran into the foam at a relative speed of about 545 miles per hour. Low density didn't mean low energy. At that speed, the impact carried roughly 22,000 joules, but the exact damage still depended on the foam's shape, angle, and where it landed. And it landed on one of the worst possible places. Most of the shuttle's underside used fragile silica tiles. The curved leading edge of each wing faced even harsher heating, so it used reinforced carbon-carbon panels. During reentry, that leading edge could reach about 3,000 degrees Fahrenheit. Behind those panels, however, the wing structure was aluminum. Aluminum loses strength far below those temperatures. The carbon panels were the locked front door. The foam only needed to break that door. No camera could show the damage clearly enough during the mission. Engineers formed a debris assessment team and tried to estimate what the strike had done. But their main software tool, called Crater, had been validated for much smaller debris and for thermal tiles, not for a foam chunk of this scale striking the reinforced carbon-carbon leading edge. The team's analysis carried major uncertainty. Some engineers wanted high-resolution images of Columbia in orbit. 3 separate requests for imagery were initiated, but they moved through confused and informal channels. Managers focused on whether anyone had a mandatory requirement for the images. One request that reached Defense Department personnel was canceled soon afterward. This is where the story stops being only about physics. Foam had fallen before. The accident board later found foam loss on more than 80% of the shuttle missions, with imagery good enough to confirm or rule it out. The specific left bipod ramp had shed large pieces on several earlier flights. The previous mission, STS-112, had suffered another major bipod foam loss. Yet those shuttles came home. Each safe landing made the next foam strike feel less like an emergency. A design requirement had quietly turned into an accepted maintenance problem. The absence of disaster was treated as evidence that the hazard was understood. On Flight Day 8, Mission Control emailed Columbia's commander and pilot a clip of the strike. The message said the event had happened before and presented no concern for re-entry. But the wing was already wounded. On February 1st, Columbia began its descent. The shuttle hit the upper atmosphere traveling around Mach 25. A normal shock layer formed around the vehicle, heating the wing edges to temperatures that would melt the aluminum inside. Superheated gas found the breach near reinforced carbon-carbon panel 8 and entered the left wing. It attacked insulation, wiring, sensors, and the aluminum structure from the inside. At first, Columbia's computers compensated. They adjusted control surfaces to counter rising drag on the damaged wing. Then temperature and pressure readings disappeared. Pieces of the wing began shedding. The flight computers demanded more correction than the shuttle could provide. Mission Control saw 4 hydraulic sensor readings drop off-scale low in the left wing. Seconds later, tire pressure messages appeared. The final radio call was cut off. Columbia broke apart over Texas about 16 minutes before its planned landing. All 7 crew members were lost. After the accident, investigators had to prove that something as soft as foam could really break the wing's carbon panels. They built a full-size section of Shuttle wing leading edge and used a compressed gas cannon to fire a flight-like foam block at it. Early shots caused cracks and displaced seals. Then, on July 7, 2003, a foam block struck a panel removed from Atlantis at about 775 feet per second. It punched a hole roughly 16 inches across. The material everyone had treated as too light to be catastrophic had produced the missing physical evidence. But the accident board's conclusion went further. The physical cause was the foam breach. The organizational cause was a system that allowed a known defect to keep flying, used uncertain analysis as reassurance, and failed to elevate the engineer's need for better images. There's one more difficult question. If NASA had recognized the damage, could the crew have been saved? The board asked NASA to study 2 emergency options. A makeshift repair using materials already aboard Columbia was judged high risk. A rescue using Space Shuttle Atlantis was considered challenging, but feasible. If managers had confirmed catastrophic damage before Flight Day 7, accelerated Atlantis's preparation, and completed a flawless launch and rendezvous before Columbia's supplies ran out. That wasn't a guaranteed rescue. It was a narrow, theoretical possibility. But it means the missing images and the failure to treat uncertainty as danger mattered. After Columbia, NASA changed the shuttle system. It improved launch imagery, reduced foam shedding risks, required better on-orbit inspection of the heat shield, developed repair techniques, and created contingency rescue plans. The deeper lesson is bigger than a spacecraft. When the same warning appears again and again without causing a catastrophe, that doesn't prove the system is safe. It may only mean the system has been lucky. Columbia wasn't destroyed by foam alone. It was destroyed by a small physical failure meeting a much larger failure to keep asking, what if this time is different?